Hello, everyone. My name is Jeongbin Park, and
My name is Chunyu Li.
yeah, so now we are talk about the project entitled Robust Markov Decision Processes, and there are two papers for our project. So we refer to the paper as the first paper and the right paper as the second paper, and they are published in a very similar time period. But even if so, the left one is the original, and the right one mainly refer to the left paper. So the motivation is as follows. Standard Markov decision processes assume known transition probabilities P. So as we have learned during the class or during the exam or homework, the transition probabilities are already given. But in practice or in reality, transitions P are estimated and may be uncertain or ambiguous. So there are two characteristics of real transition matrices. The first one is uncertainty. Uncertainty refers to uh, the fact that P is random but follows their own probability distribution, while ambiguity indicates that the P follows an unknown probability distribution. Even small perturbations in transitions may dramatically change the optimal policies. So understanding the um, uncertainty or robustness or ambiguity in the transition matrices and our project are of huge importance. So the goal is to choose a robust policy, mainly focusing on the ambiguity. So the formulation for our robust dynamic programming is as follows. So as I mentioned, we are trying to find an optimal policy achieving the supreme reward. So we can designate the objective reward value as follows. Here, as we have learned, we are considering the supremum. That is the a classical one. However, in the robustness setting, there is infimum setting. So the interpretation in an adversarial setting is as follows. So firstly, the decision maker chooses a policy phi and the adversary here, after, when phi is determined, observes phi and chooses p here that minimizes the reward. So it's kind of counterbalancing to each other. Since here as t plus 1 is ambiguous, we consider R of t as of t as a of t as t plus 1 instead of R of t as t and at. And two problems can be expected from the robust dynamic programming setting. The first problem is it's state as an action A as an inner minimization infimum stuff, right? And that can make it heavier computation than standard Markov decision process. So here the computation matters. And the second problem is if worst case choices become temporally coupled, so here t equals to 0 to n minus 1. So that temporal coupling is there. Then the inner infimum optimization loses its nice convex structure. So the convex optimization is not applicable. So the calculation of the infimum will not be feasible in real cases. This is an example of the problem for the convexity. So for example, if we are only considering the supremum, then just like what we have learned during the class or homework, we are mainly observing the convexity of the objective function or value function. However, if there is an infimum step, then now we are considering somewhat y is over infimum of two objective function or something like that. In such a case, there can be a concave property of the objective function or value function. In such a case, calculation of the infimum will not be that feasible in real cases or computation. So the rectangularity is introduced as a key assumption for obtaining the robust dynamic programming. So here we are focusing on the T phi. So T phi is a kind of set of transition matrices given the policy phi. And here we assume that can be decomposed into multiple smaller transition matrix corresponding its time point. Here, so H of n refers to the history containing multiple states and actions up to the time n. And also here, PHT means the probability of the transitioning to ST plus 1. And T to the D of T is uncertainty set under decision rule D of T. And here, Cartesian product X means each element of each tuple of a part stage distribution can be represented as follows. So it means that the choice of transition probabilities at each time is independent of each other's. It's very similar to the statistical independence, but the detailed definition can be a little bit different. So the rectangularity addresses the problems introduced earlier. The choice of a particular distribution in a state action pair at time t does not limit the choices of the adversary in the future. That is the meaning of the rectangularity. And as a result, the computation becomes tractable, mitigating the curse of dimensionality. And the second result is the rectangularity assumption resolves this by decomposing the overall uncertainty set P into convex sets for each stage and each stage action pair, so that the inner mean infimum in the robust Bellman equation is well defined and remains a convex optimization problem. So this is the first case, finite horizon robust MDP. When policy phi is fixed, then we can define the value function as follows. Here, this is the inner part of the value function. And in the end, we are considering the streamum, as I mentioned earlier slides. Since as I already mentioned about this explanation, and the reward is already certain. This is as assumed. And the Bellman equation is as follows. So in the terminal point, we can define the reward very easily, but in the backward induction, we can define the dynamic programming as follows. Here, infimum is added, so there can be the only difference with the class. So here, Bellman equation can be expanded as follows. So here, for example, here, I mentioned this one, and by rectangularity, these transition matrix can be decomposed into the transition matrix at that time point and the following transition matrix set. And then this is what rectangularity is actually working on. And here I assume that type of notations. And the following steps are very straightforward, just like what you have learned. So as a result, we can make this can be less than this one. So this is just like the comparison principle. So interestingly, two-agent setting, decision maker and adversary, doesn't affect the deterministic property of the optimal policy because the comparison principle is shown as expected. So we can find that 0 and 2 here, deterministic Markov policies can be found, and the proof is saying the result is established by induction. We have learned during the class, so I can skip that.
Okay, then for the second case, we're looking at the infinite horizon robust MDP with discounted reward. So for now, the Bellman equation is very similar to the ones that we have learned in the class, except that there's an inner problem involved, which gives us the worst case scenario by choosing the worst possible transition probability. And also, the property of rectangularity may not hold for infinite horizon setting, and we'll talk about it later. But if it's satisfied, we have the following theorem. So, okay, so if we're given an operator LD that has the following properties, so part A basically says that it's a contraction. So it has the same definition that we've learned in the class, and also given such an operator, this fixed point equation would have a unique solution, and also the solution is exactly the Bellman equation. So the proof for this result is pretty similar to what we have learned in the class, just like what is shown on the right. So even if we have the inner problem that gives us the worst case scenario, the proof would still follow a similar or the same structure. So the Bellman operator would take the following form, which is basically just like the objective function that we've seen. The supremum comes before it's basically the outer problem, and the infimum deals with the inner problem. Um, but in order to make sure the operator is actually a contraction mapping, uh, in this case, infimum should be an independent and local problem for each state action pair, and they should not be coupled with the past or the future, even if the selection of P varies according to state and time. So that would guarantee independence. So one corollary of the theorem that we have just seen is that the existence of infimum and supremum would not alter the conclusion of the Banach fixed point theorem. So given the LD operator that we have just seen, part A basically says that if D is a deterministic decision rule, and also the value is it's based on a stationary policy, and it would also have a unique solution to the operator equation. So if we were to compare the form of this equation to the previous one, as you can see, now we're not optimizing over the policies. We're basically uh, computing the value based on the deterministic decision rule. Then for part B, um, now it basically says that the value function would have a unique solution given that the it would give us a epsilon optimal stationary policy. So in order to get the optimal policies or the optimal values, just like what we've done in the class, can do that in two ways. So the first approach would be value iteration. So, okay, the second, first one should be value iteration, and the second one could be just like what we've done in the class is a policy iteration algorithm. And as for the third case, even though it's not mentioned in the paper, but we know that there exists an infinite horizon average reward robust MDP. And just like, okay, so it's pretty, so this is a table that sort of shows the differences between classical Blackwell and the new paper. So as we can see from the table, the settings are different because we're now dealing with the robust version of the problem, and the main goal are sort of not the same because we're now um, working on a robust problem. But and also the main difference between these two settings is that the idea for proof are kind of different. Because originally, we would end up with a rational function that has finitely many zeros. And however, for the robust version, we couldn't really get a rational function because of the existence of the inner problem. In this case, we couldn't really count the number of zeros. Instead, what we're going to do is that we're going to prove the uniform convergence of the of 1 minus gamma times v gamma. And then we have to swap the order of the limit and minimum. Okay, now we have just discussed that, the main difference between the robust version and the classical version is that we have to solve the inner problem. So as you can see, the part colored in red, so that would be the inner problem. So for the inner problem, the adversary or the nature chooses the P that gives the worst case scenario, which minimizes the reward. And this problem needs to be solved. So now we basically have two different models. We'll be looking at two different models. So first one would be the likelihood model, and the other one would be entropy model. Okay, for the likelihood model, so we're going to start with the empirical frequency matrix. So basically, the ijth entry of this matrix is the empirical frequency going from state I to state j. And in order to estimate the parameter p in this case, we would need to formulate everything into a log likelihood. And after we do there, we take the derivative and set it to zero, we know that the maximum likelihood estimator would be the empirical frequency. And beta x here is actually the optimal log likelihood. So in order to get the confidence region, we can try to find all the transition. So this is basically a set of all the transition probabilities that have non-zero, non-negative entries whose row sums to one, and the log likelihood being greater than or equal to a threshold beta. And this beta is basically a likelihood. So it's a likelihood that is smaller than the maximum likelihood. So so given the problem that we're trying to solve, um, we can now leverage the property of rectangularity. So based on rectangularity, we can now we only it suffices to work with one row at a time. So for now, we can sort of redefine the um, confidence region based on each row. So the confidence region corresponding to each row would be defined as sort of probability vectors sum to one, which satisfies the criterion that we have just seen. So now the inner problem, so in order to get to solve the inner problem based on this confidence region, we can sort of reformulate the original problem into the following form. So to solve this problem, so the proper procedure to do this is that we first need to formulate the primal problem by writing everything in terms of a Lagrangian, and then we turn it into dual. And after um, we can then like take the derivative with respect to p and set it to zero and make several different simplifications, and eventually we would eliminate the other. We would convert this function in three variables into a function with only one variable. So it's just a one variable minimization task. And then given a problem in this form, we can apply the bisection algorithm to find the minimizer. We can go to the next page, I think. Jeongbin?
Mhm.
Great.
Next one.
Jeongbin, can you hear me?
Yeah, I can hear you. What's going on?
I think there's a network issue.
I don't think so.
It's kind of weird.
I can hear you.
Yeah, I can hear you okay.
Yeah, let's go
But I
keep
don't know
on
why like
going.
the page kind of stuck.
Here?
Is kind of stuck. So are you
Okay.
on page 20?
Oh, wait a second. I can share that again. So
Okay.
this one or this one? This one.
Okay. We can start from this one. Yeah.
Yeah.
So this is a brief illustration of the bisection method. So given that we know, so basically bisection method is used for root finding. So given a function that we know that the root is within a certain range, we can start searching in that range. So it's, as you can see, it's an iterative algorithm. So First of all, we take the midpoint and see if the midpoint, and we evaluate the function at that midpoint. And then we check whether it's above zero or not. If it's above zero, we search the part um, that is on the left. So for this example, we search the area on the left, and then we take the midpoint again, and then we evaluate the function at that point. If it's less than zero, we take the part on the right, then we do it iteratively in the same manner. And eventually it would converge to a root. So for this problem, basically what we're trying to find is the minimizer. So for a minimizer, the derivative, given that we know this function is convex, it suffices to find the stationary point to find the global optimum. So now we're sort of converting the problem into, so we can convert this problem into a root finding problem by applying the bisection method on its derivative. So if we can find the root of the derivative, then we find the minimizer. So the only thing we need to determine is the range of searching. So now we're taking the lower bound as Vmax and and the upper bound as the form shown up there, and then after choosing a delta, we can just apply the bisection algorithm on the derivative, just like how we did it. Okay, now for the entropy models. So first of all, there's a certain metric called KL divergence. So basically, you can think of it as a sort of a distance between two distributions. So in this case, we can define the confidence region based on this distance. So given a certain distribution Q, we can pick all the distributions P that lies within the distance of beta in terms of KL divergence. And this set is considered as the confidence region. So in this case, the dual problem, so I'm showing the dual problem, and once again, it can be simplified, and we can once again apply the bisection method given these the lower bound and the upper bound, because this is once again a convex function. So for all the possible uncertainty sets that has been mentioned in the paper. So these are the computational complexities per state action. So as you can see, compared to the the classical DP, robust DP solves has a relatively higher, but not by too much. Relatively higher complexity, but not by too much.
Okay, so we discussed the applications and use cases of the robust dynamic programming, and here is the overview comparing two papers we mentioned and reviewed. So, for example, the first paper investigates a finite horizon, infinite horizon, just like the second paper. However, the second paper mentioned the rectangularity explicitly, and also it pointed out the lack of explanation of that important assumption in the first paper, in the second paper. And here the key algorithms are also different between two. For example, the first paper only explores the robust value iteration, while the second paper also explores the policy iteration. Please note that linear programming will not be that easily possible if the, I mean, easily possible without the assumption of the rectangularity. However, as we have rectangularity, the convexity of the function is established so that it also be explored in the previous slide. And the problem we discussed is very similar to the optimization rather than game. However, we can also compare our problem setting with the game theoretic setting. Please note that optimization explores the minimization or maximization of a certain function value, while the game theory explores a situation where multiple decision makers and objective functions are existent, and actually there is multiple equilibrium, which is called Nash equilibrium. And there is a structural assumption between two. Optimization assumes a strong convexity to explore the optimal value very efficiently, while the game theory only requires monotonicity. And if the convexity is met, then the optimization can result in the global minimizer, while the game theory result in a Nash equilibrium solution, which is very different from the optimization setting, because there can be a lot of Nash equilibrium, and the a certain equilibrium can be existence according to a kind of inefficient what very equilibrium state between a lot of players. So it's possible, and also the non-convexity, the solution if non-convexity can also be different between two. So I want to mention there is a stark difference between two settings. However, this problem is similar to optimization because even if it seems a two-party zero-sum game, because with Bellman operator now rectangularity, a nature choice is not really a strategy, but an infimum operator. And no game theoretic mixed strategies or best response dynamics can be observed with this setting. And also rectangularity makes a fixed point problem a Bellman operator, so which is making the problem setting very similar to the optimization setting. So and also we can think of single agent versus not multiple agent system comparison, but our problem setting is indeed a single agent system instead of multiple agent system. Because we treat the nature as, not as a strategic player, but as an oracle that always takes an infimum. The optimal policy is Markov deterministic policy. It's essentially a min-max problem with only one agent's objective. A rectangularity makes the Bellman operator well defined almost as in a standard Markov decision process. This is very different from general dynamic games where multiple agents adapt their strategies based on history. So in the second paper, I can find the lemma 3 here. Even if the adversary is trying to differentiate their behaviors by using static or dynamic or very eclectic choices, it doesn't matter. I mean, the optimal regarding the robust optimal policy, actually, the adversary has nothing to do with the final optimal value in the situation of robust setting. However, there are several limitations or open questions to note. Personally, the real application require approximate dynamic programming as well as the exact dynamic programming we have discussed in the earlier slides. So it would be valuable to develop a robust version of approximate dynamic programming to help avoid its instabilities. And also, if the transition model changes only slowly, then it becomes unrealistic to assume that nature can adversarially switch to a completely new distribution every time the same pair is encountered, especially in an infinite horizon setting where such revisits are frequent. So this is an example diagram I made, and that is reflective of the class material. And for example, here we can think of infinitely many nodes, and we can visit from 1 to 2, 2 to 3, and 3 to 2. In such a case, the policy, I mean, can be only considering the neighboring nodes given a node. So it is not satisfying the rectangularity, because the rectangularity mentions very independent policy or transition metrics can be assumed, but in such a case, the given node is very important. So infinite time horizon setting can be problematic regarding the rectangularity. However, the author also notes that nature's ability to vary its choice at each step becomes less problematic when the stationary policy itself does not vary over time. So the stationarity of the policy itself can be a little bit like alleviating factor for the difficulty of defining the rectangularity. Thank you.